Good evening, all. Let's wait for a couple of minutes for a few more people to join, and then we'll get started. So this week we will be discussing on first law of thermodynamics. Most of the problems are related to first law of thermodynamics, and one question for a discussion, which we will take up at the end of the session. While we are waiting for other people to join, so we can go through the first question, the first problem here. So there is a particular stone that is around 15 meters from the water level. This is a tank. So as the stone is falling from this particular height to the tank, so this center point is the center of the stone. So as it falls, eventually it will drown into the tank and it will come to rest at when it hits this one. We are saying that as the stone is moving from the surface to the bottom, eventually it gets to rest by the time it goes to the bottom. It's not like the stone is hitting the bottom with some velocity. The velocity of the stone before it hits the bottom is zero. Now in this scenario, we are asking to use first law and determine the change in internal energy, potential kinetic energy, heat loss, and work done in different cases. The first one is before the stone enters the water, that is just about the point when it is about to enter the water, and when it has come to rest inside the tank. In both of these scenarios, in the final part is asked such that the heat is transferred to the surroundings in such an amount that the stone and water come to their initial temperature. So initially, both are at some particular temperature, let's say 25 Celsius. Now, as the stone is moving through the water, it comes to rest after a certain point. So when it comes to rest, we are saying that some heat is lost from the surrounding. So this is the boundary, the dotted line. The dotted line shown here is the boundary. So across this boundary, we are saying some heat is transferred such that both the stone and water come to their initial temperatures. That is say 25 Celsius. So if that is the case, what is the heat transfer? How do we solve such problems? So anyway, the first step in any of these problems is to start with your first law. So what does first law tell us? The net change, the net heat transfer across the boundary. So this is my boundary. Is the net change in internal energy, the net change in energy plus your work done by the system, where this delta E is composed of several quantities like delta U plus change in kinetic energy, potential energy, the change in internal energy, kinetic and potential energies. Now, in the first problem, when the stone is about to enter the water, so basically the stone is not touching the water, so uh, there is no energy transfer from the stone to the water before it touches the surface of it. So till up until that point, we do not have any work transfer because there is no interaction. If you consider this boundary as your system, there is nothing external to the system that is changing because of the stone falling into this one. If instead, for suppose, imagine in this way, if this stone is connected to a string and that string is connected to some pulley or something like that, in that scenario, what would happen? As the stone moves down, if the pulley is actually, if imagine something like this, imagine having some pulley here and a mass connector, something like this. If you have something like this, what would happen is as the stone falls down, it is actually getting converted into a work here, which is something which is not happening here because we haven't connected that to anything. So even if there might be some work, we are not actually utilizing it. Since we are not utilizing, there is no net work done by the system. My system is everything inside this boundary. If this boundary is whatever is inside this is not doing any work on the surroundings. So we are saying the work done is zero before it touches the water, or even as it goes into the water, as it moves throughout the process, work done will be zero because it is not connected to the surroundings in any way except for the air movements, which is not causing any work done. So what can I say about the other quantities? So what about the Q? So before there is any interaction between stone and water, it's assumed that the water and air, everything is at the same temperature. So there wouldn't be any like heat transfer. If we recall from the original first lectures, heat transfer is caused only because of your temperature difference. And here we are saying initially everything is at the same temperature. So here we have specified here, if you see the stone and water are at the same temperature initially. initially they are at the same temperature. So if there is no temperature difference, then there wouldn't be any heat transfer. So the heat transfer is also 0 before it touches the water. So if there is no heat transfer and no work done, and there is no change in temperature is not happening, since U is a property and it only depends on the initial and final states. If the initial temperature is same as the final temperature, that means the temperature at this point and the temperature just before it touches water is the same. So delta U is also 0, which leaves us with delta KE plus delta PE, that is change in kinetic and potential energies, is equals to 0. So as the stone is falling from the top to the bottom, so its potential energy is getting converted into kinetic energy, so that the net change is actually 0. So we can calculate the change in potential energy. So as the stone is falling from a higher height to a lower height, so from a higher elevation to a lower elevation, the potential energy will decrease. So I'm just putting a minus here, minus the mass of the stone, G times whatever is that H. So the stone mass is 20 kilogram, G you can take out to be 9.81, and the height is 15 meters. This gives me around 2943 joules. This is the change in potential energy, and this is negative because the height is getting reduced. Now, from this from the first equation, or maybe I'll call this number 1, this as number 2. So from equation 2, we can say that delta change in kinetic energy is negative of change in potential energy, which is 2943 joules. So this is clear. Now what happens when the stone has come to rest inside the tank? Now the stone touches the water surface and it starts moving into it. So as it goes down, it's actually slowing down, and eventually it will come to rest at some particular point. So before it comes to rest, so at the point where its velocity becomes 0, so what will happen? So as we said before, work done is going to be 0. Why are we saying work done is 0? Is again because it is not connected to the surroundings in any way, so we cannot extract any work from it, any work from this particular system. So work done is 0. And what is the change in? So once it comes to rest, what happens? Like this stone comes here. Let's say eventually it comes here and sits at the bottom, somewhere here. If it is sitting at the bottom, at that particular point, its velocity is 0. So once it reaches there, so what do you say about your change in kinetic energy? So once it comes to rest, I can say that after it comes to rest, the change in kinetic energy will be 0 because its velocity is not changing. The change in potential energy is what we have already calculated before. So this change in potential energy, whatever potential energy change that has happened before, should be entirely converted into my internal energy, and these are the only two changes that are happening, and this should be equal to 0. From our first equation, since Q is 0, because there is no net heat transfer across the boundary. So there is some heat transfer that could be happening internally, but this is my boundary. Across the boundary, there is no heat transfer. So as there is no heat transfer across the boundary, no work done, so both of them to be 0. And we are saying that it has comes to rest, so change in kinetic energy is 0. So we have only change in potential energy that is getting converted into change in internal energy. So what will happen here? We already calculated delta P, so delta U will be negative of delta P, so that is 2943 joules. So what does this mean? So we have a net increase in internal energy. Since it is a property, it means that delta U is positive, which means temperature will increase. And this delta U is for the total system, that is stone plus water plus tank, everything combined. So all of them combined, the delta U has increased by certain amount. So your temperature of the entire system will increase. Now previously, the stone, water as well as the surroundings are at the same temperature. Now what? So there is no heat transfer across this interface. But now when the stone has come to rest, where the total potential energy, whatever the loss in potential energy, is converted into the internal energy of the entire system. So the temperature of this entire system increases. Now there is a temperature difference between the system across the system boundary, because of which heat flow happens. Now how do we calculate that heat transfer? So if we use the same equation that you have before, so my net heat transfer will be delta U, whatever is my net change in energy, plus W is anyway 0, so I'm not writing that down. Just to be consistent. So this is 0 because we don't have any changes. My net change in energy is something that I've calculated before. Now we are saying that heat is transferred to the surroundings in such an amount that the stone and water came to the same initial temperature. So if both of them are coming to the same initial temperature during that particular process, so what we are saying is initially you are at temperature T. When after the stone falls, you went to some temperature T1. So from T0 to T1, and then finally you are coming back to the same temperature T0. So from this to this, we know delta U is given, which we have calculated in part 2, it is 2943 joules. Now we are saying the heat is transferred to the surroundings in such an amount that the stone and water come to their initial temperature. So in the second process, your delta U has to be decreased by the same amount so that you will come back to the same initial state. So what should be the heat transfer here? So for this second process, we have del Q equals to delta U plus del W, where there is no work transfer, and this delta U should be such that you return to the original state. So your del Q in such a, so this will be minus 2943 joule, because you have a increase in internal energy in the first state from T0 to T1. Now you have to decrease that internal energy by the same amount so that you can get back to the original state. Since U is a state function, it only depends on the initial and final state. So this amount, this value is going to be same for process 0 to 1 and 1 to 2. So this is negative of 2943 joule. Now the total Q, since work done is 0, and once the stone has come to rest, delta KE is 0 and delta P is also 0 after the stone has come to rest. So you have to remove 2943 joules of energy from this system so that it will be at the same initial temperature as it was when it is at 15 meter above the water surface. Is this clear? Yeah, I hope it is clear. There are no questions. Then we'll go to the next problem. So here we have a system which is taken from particular state L to state M along with a path L, Q, M. And during that particular process, 168 kilojoules of heat flows into the system. So if you were following the notation, heat taken out of the system is given negative value, and input to the system is considered to be positive. Similarly, work done by the system is positive and work done on the system is negative. So if we go with that logic, so Q during the process L, Q, M, heat is added to the system. So it is a positive value of 168 kilojoule. And the system does 64 kilojoule of work. Work done by the system is positive. So work done during the process L, Q, M is plus 64 kilojoule. Now with this information, we will proceed for the next parts. So the first part asks you how much will be the heat that flows into the system along the path L, N, M if the work done in the process is 21 kilojoule. So this problem only resides on knowing one fact, that your internal energy, change in internal energy, is a state function and it doesn't depend on the path you are following. So as long as you as long as you know that the points L and M are fixed, and if I can calculate delta U between L and M, then it doesn't matter which way you go. You go from L to M along this path, or LQM or LNM, whichever way you go, the change in internal energy is going to be the same. So The first part of the question asks you if work done along the path LNM is 21 kilojoule, you are asked to find the heat along the path QLNM. So QLNM is given by, you are going from L to M. So your delta U will be UM minus UL plus WLNM. And how do I get UM minus UL? I can use the information given previously. So QLQM is given by UM minus UL plus WLQM. So both the Q and WLQM are given. So this leaves us with UM minus UL equals to Q minus W. So that is 168 minus 64 plus 104 kilojoule. Now with that, we know the value of UM minus UL. You can substitute back in the original equation to calculate QLNM. So QLNM is 104 plus 21, which is a positive value of plus 125 kilojoule. Now coming to the second part, when the system is returned from state M to L along the curved path, the work done is given by 42 kilojoule. So work done along the path M to L. It is specified that work is done on the system. So following the same notation that we have followed before, work done on the system is negative. So this is minus 42 kilojoule. Does the system absorb or liberate heat, and how much of the heat is absorbed or liberated? You already know delta U. So if you want to find Q M to L, that will be given by U. Here the final state is L, like you are moving from M to L. So final state is L and initial state is M. So delta U is given by UL minus UM plus WML. I've already calculated UM minus UL as 104. So this will be negative 104 and WML is also negative, which is 42. That gives me a value of minus 146 kilojoule. So since it is a negative value, it means heat is being liberated from the system. Heat addition to the system is positive, so here it is going out of the system. Now coming to the third part, if again as we said before, your UL and UM are state functions, so we are just saying an arbitrary reference. So if suppose UL equals to 0 and UM is given to be 84 kilojoule, find the heat absorbed in the process Ln and Nm. So how do we do that? So it is a PV diagram. So in a PV diagram, along the path Ln, if you observe the path Ln, it is a constant pressure process. And Nm, if you see this particular one, Nm is a constant volume process. So we can write WLNM to be Ln plus Nm. So the net work done in case of a PV diagram, as we have defined previously, work done is integral PVdV, which is area under the curve. So along the process Lnm, so okay, here the arrows might be different, but let's say you're going along this direction, Lnm. So along that particular process, your net work done is area under it. So I'm just dividing it into two parts. So the area under the first part Ln and then the Nm part. Now since this is a constant volume process, Wnm is 0. So this goes to 0 and this is equals WLN, which we have already had the value previously as 21 kilojoule. So now for the process Ln, do we know anything about the process Ln? It's a constant pressure process. So how do we calculate it for that? QLNM QLN is delta U between final and initial state. So that is UN minus UL plus WLN. UN minus UL is provided here and WLN we have calculated just now. So this gives me a value of plus 105 kilojoule. And if you take the other one, that is QNM, is the final state minus initial state, UM minus UN plus WNM. Since it is a constant volume process, WNM is 0. So UM we already have the value. So like UM, UL is provided to be 0. So UM minus UL is equal to, or I'll just write for consistency, UM minus UL plus UL minus UN. So UM minus UL we have as plus 168 and UL minus UN we have minus 84. So thus we have the final value of heat transfer along the path L and M. Okay, are there any questions? Okay, I guess there are no questions, so we'll go to the next problem. So these are a little bit more mathematical ones. So here you have a fluid system which undergoes a non-flow frictionless piston following the pressure volume relation as P is 5 by V plus 1.5. P is in bar and V is in cubic meters. So where do you find such systems? We'll not get into that, but think about it. So think about the process that can give you these kind of scenarios. So what is happening here is PV is not a constant thing. Instead, it is a constant plus something which is a function of volume. So it's not an isothermal process, but it is something slightly different from it. Think about the scenarios where you can have scenarios like that. And during this particular process, the volume changes from an initial of 0.15 meter cube to 0.05 cubic meter. So this is a compression process, and the system rejects 45 kilojoule of heat. Determine the change in internal energy and change in enthalpy. Okay, so how do I calculate change in internal energy? Again, all of these problems are based on first law. So if you have one unknown, you can get only one equation. The one equation that you are going to be using here is the first law. So your the net heat transfer is given by work done plus change in internal energy. I'm just avoiding the delta before Q and W just for clarity. So Q is already provided to be 45 kilojoules and it is heat rejected from the system. So Q is negative. So in order to find delta U, this is something that I need to find. So to find that, I need to calculate W. So we already know W to be integral PdV between initial volume and final volume. So in this case, it is given that my pressure is varying with volume in this particular fashion. And my initial volume is 0.15 to a final volume of 0.05. If you do the math, I'll just write one more step. So here, just to be consistent with the units, volume is in cubic meter and pressure is in specified pressure is in bar. So whatever I get here, if I multiply with 100, so this will get converted into kilojoules. So that gives me a value of minus 564.306 kilojoules. Now I have my work done and my change in my heat transfer. So I can calculate my internal energy change as Q minus W. That gives me a positive value of 519.36. So here there is an increase in internal energy, which means your temperature is going to increase. Now coming to the next point, how do I calculate the change in enthalpy? So what is enthalpy? Enthalpy is again a property. It's also like property is a state function. H is U plus PV, which is specific one, or if you can write it in the general one, H is U plus PV. So I'm asking delta change in enthalpy, so that is delta H is delta U plus delta PV. So we will do that. Again, to reiterate the fact that H is a property or a state function. It only depends on the initial and the final states. It doesn't depend on the process in which you are following, which means this will be delta U is the one that we have calculated before, plus this is going to depend only on initial and final states. So that is P2 V2 minus P1 V1. So delta U we have already calculated. Final pressure is pi by final volume minus initial volume. Again, just to be consistent with the units, the delta U is calculated in kilojoule, but here pressure is in bar, so I'm multiplying with 100 to convert it into kilojoules. So this gives me value of plus 504.306 kilojoule. Again, whenever you are asked to find change in enthalpy or internal energy, these are state functions, so they are going to depend only on the initial and final states. You don't have to worry about the process in which this is happening. So that's exactly the reason you are not given the process. Even if the question says you that it's an isothermal process or adiabatic process or whichever process it is, it doesn't matter. These values of delta U and delta H are going to be the same. The only thing that is going to differ is if the process were different. If it follows a different process, instead of the particular one that is shown here, if it follows a different process, then your heat rejection is going to be different, and accordingly your other values will be changing. So heat rejection will change, so your work done will change, but then delta U will remain the same. Similarly here, since delta U remains the same, the P2 times V2 and minus P1 times V1 is constant. You can observe that even from here. So you see the relation, P plus 1.5, or maybe we'll just stick to this one. So these properties will change in such a way that this remains constant, and delta H is also going to be same as long as you maintain the same initial and final states. So if the initial and final states are different, only when the 2 points are different, that is when you are going to have different values of delta H and delta U. Okay, are there any questions? Excuse me. Okay, I guess there are no questions. So we'll move on to the next problem. So here we have a new equation. So unlike all the problems that we have discussed up until now, here it says that the internal energy of a certain substance is following this particular relation, where the specific internal energy is given by 3.64 times P is pressure, V is a specific volume, plus some constant 90. A system is composed of for 3.5 kilograms of this particular substance, and it expands from an initial pressure of 500 kilopascal and a volume of 0.25 cubic meter to a final pressure of 100 kilopascal in a process in which pressure and volume are related by the following relation: PV to the power 1.25 is constant. So this is again your polytropic process where the index of expansion is 1.25. First part, if the expansion is quasi-static, so when we mean quasi-static, it means that it is in equilibrium at each and every point during the process. That is exactly when you will be able to come up with a relation like this. If it were not quasi-static, then this relation would not be valid. Find Q, delta U, and W for the process. So how do I start? So we know one relation. Q is given by delta U plus W, but this is only one equation, and we do not know anything about the other stuff. So is there any way to get the other values? So it is specified that it is a polytropic process. So we know work done in case of a polytropic process is given by, so if you have PV to the power n as constant, in that particular process work done is given by P2 V2 minus P1, or since in this particular case the system mass is also constant, this is equivalent to saying P V to the power n is constant. So my work done in that case is P2 V2, or if you can recollect, we have derived this previously, just for those of you who missed that. So how do we calculate work done? So we have PV to the power n equal to constant. Let's say K is a constant. The work done is given by integral PdV between V1 to V2, where P is given by K by V to the power n dV. This gives us K V to the power minus n plus 1 and minus n plus 1. So you can write K as PV to the power n. So that is, I can write K as P2 V2 to the power n times V2 to the power minus n plus 1 minus, again I'll write K for the second term as P1 V1 to the n, V1 to the power minus n plus 1 or minus n plus 1. So this leads us to this equation, P2 V2 minus P1 V1 by 1 minus n. That is my net work done. I know my initial pressure, I know my initial volume, I know my final pressure, and I also calculate the final volume using this particular relation. So from there I can use this to calculate the work done. So what is the final volume? So from this I can calculate the final volume as P1 by P2 times V1, initial pressure by final pressure times the initial volume. This gives me a final volume of 0.91 cubic meters. So now that I know the final volume, I can calculate the work done. I will just substitute in the formula. Just note the units. So just to be consistent, I am using everything in kilojoules. So I am just using the pressure value in kilopascal directly, so that your final answer will be in kilojoules. So P2 is 100 kilopascals times V2. This will be in kilojoules. So I have calculated the work done. So the next part is to calculate the change in internal energy. So delta U is given by U2 minus U, or here U is a specific internal energy, so our mass is constant. So M times U2 minus U1 is M times the mass is given as, internal energy is given as 3.64 It only depends on the initial and final state, V2, V2. The 90 gets cancelled off because it is a constant, minus V1, V1. So this gives me already know the values of V1, V2 and V1, V2. You just substitute that. So you calculated the work done. You know the value of change in internal energy. So we can calculate Q from the first law. Q is delta U plus W. This is for the first part. The second part is in another process. So the first process is a quasi-static process. Now if there is another process, the same gas expands according to the same final state as in part 1. So initial and final states are the same. However, it says that the heat transfer in the second case is 32 kilojoules. So you're saying that the initial and final state are the same. So your delta U should remain the same. Delta U same as whatever we obtained previously, that is minus 123.76. And heat transfer is specified to be, but the heat transfer in this case is 32 kilojoule. So which means the work done is given by now as you can see this work is different from the previous one that we have obtained. So previously we got a value of 136. The work done in case of part 1 is 136 kilojoule by the system from the fitting plus, and work done in case of second process is much higher than the previous case. These values are different. So again, as we've been reiterating the same fact that U is a state function, Q and W are depend on the processes. So they are not state functions. They are the path functions which depend on the process that takes place. Now, so in the in a quasi-static process, you have this particular relation that is holding up. But for suppose if it is not undergoing a quasi-static process, or there could be several other processes that is happening, and all we know that this is a heat amount of heat transfer, then work done will anyway be different from it. Even though the initial and final states are the same, the work done will be different in this case, like the ones here. Okay, are there any questions? Okay, if there are no questions, then we'll move on to the next problem. So Unlike the previous one, here we have given specific heat, which is again varying with temperature. Let's see the problem. So the properties of a system during a reversible. So again, keep note of these things. So you have a reversible process. So reversible, constant pressure, a non-flow process. So like in the previous problem, we are saying non-flow. We are highlighting this much often because we will discuss in the coming sessions what happens when flow comes into the picture. We'll derive something called steady flow steady state energy equation, and then we'll do control volume analysis, which is not the problem here. Or to put it simply, when you have a flow that is happening, flow essentially means some mass is crossing the boundary, then your system approach fails. So up until now, whatever problems we are discussing is based on system approach. So just to be consistent, we are specifying in the problem that it is a non-flow process so that you don't have any mass transfer across the boundary and you can use a system approach. At initial pressure of, okay, coming back to the problem. So you have an initial pressure of 1.6 bar changed from initial, okay, this is specific volume of 0.3 cubic meter per kg to and in temperature 20 Celsius to a different value of 0.55 cubic meter cube per kg to 260 Celsius. The specific heat of the fluid is given by this particular relation. Usually it will be specified in terms of Kelvin. This particular relation is given in Celsius. It is specified here. So you need to calculate the total heat added, change in internal energy, work done, and change in enthalpy. So how do you proceed with it? So first thing is we know that it is a reversible and a constant pressure process. So in a constant pressure process, so heat added is given by CPDT. This relation is valid, again noting that this relation is valid only for a constant pressure process. As again I have been reiterating a lot of times that Q is a path function, it depends on the process that which happens. So in a constant pressure process, it is CPDT. In a constant volume process, it will be CVDT. If it is any other process, then you might have to calculate the delta U W, and from there you need to calculate the value of Q, or in some other way you have to measure it. So always be cautious when you are using any direct relation for value of Q, because this is a path dependent function. You need to know the process that is happening from initial to the final states. So here we know the value of Cp. So initial temperature also is given as 20 to 260. Just a bit of digression here. So when we were discussing during the lectures, it was specified that Cp is, so how did we define Cp? Is basically del Q by del T at constant pressure, or if you would like to say it in terms of enthalpy, so we define in terms of del H del T at constant pressure. So usually up until now, when we were discussing anything, say in case of air, so we came up with a relation for Cp, Cv, and R in terms of the gamma of air. So what was the relation? So Cp is given as gamma R by gamma minus 1. So gamma is a constant, R is a constant. So this turns out to be a constant. But in this particular problem, it is specified that Cp is not a constant and it is actually changing with temperature, which is true for most of the real substances. Cp is not a constant, but it can changes with temperature. So why do you think this changes with temperature? Maybe something internally changes. So you can think of this as, say, this gamma value changes because some other modes of vibration get activated at higher temperatures. As your temperature increases, the contribution of the vibration and other components to the overall internal energy will increase. That will actually change your value of Cp Cvs. So it then becomes a function of temperature. So this is one of those type of materials that we are discussing here. So in this system, we have a component which whose specificity is actually varying with temperature, unlike the ideal gas in which Cp is a constant, which is not a function of temperature. Even if you use such steam tables, which we were using a couple of weeks back, so in the steam tables, you can look up the values of in the superheated state, and then you see that it will be more or less constant, and you can use ideal gas assumption for that. But then if you see it at very high temperatures, and you will also notice that there are some deviations in it. You can check that and maybe come back in the next week. Okay, now coming back to this problem, so we do the integration. So this will be 1.5 times t. Since t is in Celsius, I'm using directly the Celsius values. This is the first part, the heat added. How do we do the second problem? So the next problem asks you to calculate the work done, which is straightforward. So work done is, again, all of these are per kg of per kilogram of the substance. The work done is again integral PdV. It is a constant pressure process, and the pressure is specified to be 1.6 bar. Just to be consistent with the units, I'm multiplying with 100 so that you'll convert it into kilojoule into final volume minus initial volume. So the final volume is 0.55 minus the initial volume is 0.3. These are specific volumes, and obviously the work you would get in kilojoule per kilogram. So you have 1.6 per kg. Now, what about the next problem? Is change in internal energy. You have Q and W, so this is straightforward. You just do Q minus W. Now, how do I calculate change in enthalpy? Just as we have done in the previous problem, change in enthalpy is change in internal energy plus change in PV. Like H is defined as U plus PV, or just to be consistent with the notation, I'll just put a little bit here since U is in kilogram per kilojoule per kilogram. So the delta U you have already calculated, and P is a constant, so that this comes out. So that will be P times delta U plus P is a constant, so it just comes out times delta P. So this is as a, since it is a constant pressure process, this is essentially the work done. You have delta U plus work done, which is again giving you Q. So Q in this particular scenario where you have a constant pressure process, the Q is given to be equal to change in enthalpy. So, and which is equal to the value we have already calculated. And hence the relation that we have used before. Cp is defined as del H del T at constant Q or del Q del T at constant, whatever you call that. So your H will be equal to Q under in the case of a constant pressure process. Okay. Are there any questions in this? We'll pause for a couple of minutes since we are halfway into it. So if you have any questions, we can discuss. Wait for a couple of minutes so you can just go through what we discussed now. If you have questions, raise your hand or you can post it in the chat box. Okay, I guess there are no questions, so we'll move on to the other problems. Okay. Moving on to the next one. So here you have a movable frictionless piston that is inside a fully insulated cylinder. So this there is no heat transfer across it on one side and offers a constant resistance during its motion. So why are we saying it's a constant resistance? So when we say it's a constant resistance, it means that the pressure external to it is actually remaining constant. So that you can assume it to be a constant pressure process. A paddle work is drawn into the cylinder and does work on the system. Okay, sorry. So you have a paddle wheel that is rotating, which means it's actually doing some, you're externally doing some work on the system. So determine the paddle work in terms of delta H. Just as we discussed, so if you apply the first law, delta U plus W, where your work done, now the entire system is insulated, so your Q will be 0. Now what are the components of this work done? So work done has two components here. One is this expansion, that is the piston work, and the other one is a component of this paddle work. So I'm just splitting it into two parts. Now work done by the paddle is going to be minus delta U minus work done by the piston, or basically the piston component of the work done. So the piston is, as this is rotating, this thing is heated up. So if imagine you are stirring a tea, then it gets heated up. So as you stir this up, these contents get heated. Since it is insulated, temperature will increase. So since it is the next important point here is it is mentioned that it offers a constant resistance, which means the pressure is constant. So in a constant pressure process, if your temperature increases and your volume increases, so this expands. So work done by the piston can be written as P times whatever is the change in volume that you are going to have. So I can write this as, so since this P is constant, I'm just taking it inside. So this becomes minus delta H, just as before. So work done by the paddle is minus delta H. Delta H in this case is since delta U temperature is increasing, so delta U will be positive, and accordingly in this case the volume is also increasing, so both this and this terms are going to be positive. So delta H is positive, so work done by the paddle is going to be negative. So essentially you can say it directly even without this analysis, because as the wheel is rotating, you are externally supplying the work, so work is done on the system, so you are getting a negative value, so which is also consistent with whatever we expected. So the paddle, so again, as it comes out, it's a constant pressure process. So in the constant pressure process, any external work that you are doing will be equal to the change in enthalpy. So in the previous problem, when we discussed your work done, sorry, your change in enthalpy is equal to your net heat transfer. In this problem, we encountered a case where your net heat transfer across the boundary is 0 since it is insulated. Then the net interaction that is happening is only work, and that is equal to change in enthalpy. This is something that you might find tricky, but you'll understand later that any of these things, that any interactions that are happening at the boundary will have certain relation with the change in enthalpy. So in the previous case, we do not have any net interaction of work previously. In this problem, we do not have any net heat transfer, so work is equal to delta H. In previous case, Q equal to delta H. Now, if you happen to have a scenario where you have both the heat interaction as well as work interaction at the system boundary, then how do you think that will get related to H is something that we will discuss in the coming weeks. Okay, is this clear? Are there any questions? Feel free to type in the chat box if you have any questions. Okay, I guess there are no questions. So we will move on to the next problem. A 0.2 cubic meter of air at 4 bar pressure and 130 Celsius is contained in a system. A reversible adiabatic expansion takes place till the pressure falls to 1.02 bar. The gas is then heated at constant pressure till enthalpy increases by 72.5 kJ. Calculate the work done and the index of expansion if the above processes are replaced by a single reversible polytropic process, giving the same work done between the same initial and the final states, taking Cp as 1 kJ per kg Kelvin and Cv as 0.74 kJ per kg Kelvin. So it is often helpful sometimes, it is often helpful when you draw it in some kind of a PV chart or something to understand these processes. So if you see, if I were to draw it on a PV plot, so initially you were at a certain pressure, 4 bar, and final pressure is 1.2 or 1.02 bar. So let's say this is my P. So it says that it is a reversible adiabatic expansion, so volume will increase. So somewhere from here, we know the initial volume, 0.2 cubic meter. We don't know the final volume, but we know that it moves from 4 bar to 1.02 bar, but it's expanding to some particular point, which we don't know. So it is going some adiabatic expansion process. Let's say this is the problem. And then once it reaches this particular point, it says that the gas is then heated at a constant pressure. At constant pressure, if you heat, the temperature will increase, so volume will increase. So you'll again move from here to a new volume, but in a constant pressure process. So let's say this is V2 and this is V3. And it is a constant pressure process. So here pressure is 1.02 bar, but we don't know value of V3. But this change is indirectly given to us, saying that the enthalpy increases 72.5 kilojoules in the second process. So this is 0.1, 2, and 3. So 2 to 3 is a process. It's a constant pressure process where the enthalpy increases 72.5 kilojoules. Then it asks you to calculate the total work done, and we'll come to the second part a little later. Now let's get started with the first part. How do I calculate the total work done? You can use the first law and say it is Q minus delta U, which if you would have known the initial and final states, then you would have calculated delta U, and then you have to calculate Q separately, which is not advisable now, because in order to calculate Q, you would again need W. So we'll use the traditional relation. W is given by integral PdV, where between the process 1 to 3. So here we have two different processes. Essentially, I can split this integral as from 1 to 2 and from 2 to 3. So what is happening in process 1 to 2 is the reversible adiabatic expansion. So for a reversible adiabatic expansion, our process equation is PV to the power gamma equal to constant. For air, we can take gamma to be 1.4. So if you use this relation, like it's very similar to your polytropic expansion, the only difference here is the index of expansion is gamma instead of the value of n here. So you can take n to be 1.4. So what is the work done in process 1 to 3? Sorry, 1 to 2. Or I'll just directly write the equation since we have derived it in the session in the beginning of the session. So you can go back to the video to see the derivation. So it will be instead of n, it will be gamma. So in order to evaluate this, I would have to know the values of V2 and V1, which is something that I know the initial volume, but I do not know the final volume. But I know the final pressure, so I can use this relation to calculate the final volume. So I have P1 V1 to the gamma, P2 V to the gamma. So from this I can calculate V2 directly. Now that I know all these values, I can substitute them back here. So 100 is just for conversion of units. This could be one way of calculating it, but you can also try it in a different way. You know that the process is happening, you know the initial state and final state. So you can calculate the initial and final temperatures, and U is going to be Cv delta T. So you can calculate, Cv is already given here. So you can calculate Cv delta T. And since it is an adiabatic process, Q equal to 0. So you can calculate W123 even in that way. But for that, you need to calculate the final temperature. Instead of volume, you would be calculating the final temperature. So what would be the relation you will be using? So initial temperatures are given. So you use a relation between pressure and temperature. That will be like just 2 PV per gamma equal to constant. So here instead of P, you would be replacing with P by P. So from this you get P power 1 minus gamma times P per gamma equal to constant. So you will use this relation. So from this you will calculate T2. And once you get T2, you will use delta U as Cv times T2 minus T1 times the mass of it. How do I calculate the mass? So we know the initial pressure, volume and temperature. So mass can be calculated as PV by RT. You know all these properties, so you can calculate the mass. Once you get the mass and final temperature, you can calculate delta U. And Q is from 1 to 2 is 0. So W1 to 2 is minus mCv T2 minus T1. You can do that way as well, and you can try it out. So and see if this value is matching with the value that we have obtained here. I will leave that as an exercise for you. So this is for the first process, that is the adiabatic process. Now what is happening in the second one? From 2 to 3 is a constant pressure process. And it is given that delta H is 72.5 kilojoule. What is delta H? So my objective is to calculate W223 is Q 223 minus 223. So it is a constant pressure process. So Q can be written as if I write M Cp P3 minus T2 minus the internal energy is anyway state function, so that is going to be mCv T3 minus T2. So m T3 minus T2, we have Cp minus Cv, that is R. The work done in process 2 to 3 is given by mR T3 minus T2. So out of these properties, we can use the ideal gas law again. So mR T3 is P3V3 minus mR T2 is again to use ideal gas law. So this is what you get. So I know the value of P2 and V2. So I know P3 equals to P2 since it is a constant pressure process. Which is same as the expression that we would get if you were using the other form. You directly use PdV since it is a constant pressure process. So this is like whichever process you use. You can either use from Q and U, or you can use integral PdV, whichever you are convenient with, and from there you can calculate the work done. So in order to do this, I need to know the states. So P3 or the final pressure is already something that is given as 1.02 bar. V2 we have calculated just before. So what is delta H? Delta H, just as we have defined before, is mCp delta T. This is specified to be 72.5. Using the relation which we have before, this particular relation, we can calculate T2. So basically P2 power 1 minus gamma, T2 power gamma, P1 1 minus gamma, T1 1 minus T1 gamma, where T1 is something that is specified as 130 Celsius. So when you use any of these relations, it should be in Kelvin. So from this I can calculate T2. Now I have my T2. So how do I calculate M? Just as before, use ideal gas law. So M is PV by RT. Initial pressure is 4 bar. Initial volume is specified to be 0.2 cubic meters. R for air, you can use a value of 287. Again, just to reiterate, this R should be in kilojoule per kg per Kelvin, like not the value of R that you would use usually. 8.314 is with respect to moles. We have to convert it into the rate. So you can refer to the last week's lecture where we were discussing, like, after you assume that air has a certain percentage of nitrogen, oxygen, CO2 and argon gases, the percentages are usually specified. And from there, you can calculate the R value, equivalent R value for all of these combined, and equivalent molecular weight as well. So the value comes to around 287 kilojoule per kg Kelvin that I am using directly here, times your temperature, initial temperature is 403. This gives me a mass of 0.69 kilograms. So if you substitute that back here, we would get a value of P3 CP is 1 kilojoule per kg Kelvin. So now that I have calculated P3, I can directly use this relation to calculate the work done in the next process. The total process is given by MR T3 minus T2. Okay. Excuse me, I think I might have made a small mistake. So we have Cp given as 1000 joule per kg Kelvin, and Cv is given as 714 joule per kg Kelvin. So using these relations, you can calculate R directly from here. R is given by Cp minus Cv. So this gives me a value of around 286 joule per kg Kelvin. So you should be using this value instead of 287. So it's again quite close to the value we got last week. I don't think that would change my final answer drastically. So you know the value of M, 0.69 times you know the value of R. I'm just dividing with 1000 to convert it into kilojoule times T3 minus T2. This is in the process 2 to 3. So now the total work done is 1 to 2 plus 2 to 3, the reversible adiabatic process plus a constant pressure expansion process. So that is given by the previous case we have a 64.85. This is the total work done. This is the first part of the problem. The next part tells you that if suppose if you want to combine both of these processes into a single process, and you want to say that single process as your polytropic process. I think one of you have actually raised a question in the discussion forum as well, asking what a polytropic process is. So these are something like this. You have two different processes here, a reversible adiabatic followed by a constant pressure process. Now if you want to combine both of these processes into one process, and write it with an equation describing that particular process, we are using a polytropic process where you denote PV to the power n equal to constant. Now we need to find the value of n. So probably in the second week of the lectures, we discussed one way to determine this. Is basically you plot all the different values of pressure and volume, and then you fit a linear regression, or basically convert it into logarithmic form, and then do a linear regression, and then find the value of the exponent. Now there is another way to go about this, something that we'll discuss now. So if you want to discuss the linear regression method, you can refer to the week 2 lecture in the live sessions. Now the other way to go about it is you already know the work done in case of polytropic process given by P3 V3, the final state, minus P1 V1 by 1 minus n. This n is your index of exponent. So P1 V1 is something that is already specified to you. P3 is something that is already given in the problem, and V3 is something we have calculated, or we could calculate. Previously we have calculated the T3, so you can calculate V3 using the ideal gas equation. V3 is given by or maybe just to be consistent, this is a value of 286. So now we have all these values. We also calculated the net work done before. So the net work done is 85.584. This is in kilojoule. So just multiply with 100 to be consistent with the units. The 1 minus n. This is the index of exponent. Basically, you equated the work done with the relation that you have derived for a polytropic process. So if you want to represent these combined processes, the reversible adiabatic plus a constant pressure process, in this particular scenario, you can also represent it using a polytropic process where you have PV to the power 1.064 equals to constant. This process, if you were to, between the same initial and final states, if you calculate the work done, you are going to get the same value of your same value as you have gotten previously with this decomposition. Are there any questions? Okay, I guess there are no questions. So we'll move on to the next problem. It's more of discussion one. So the next one is, okay, we have a couple of more problems. So it's again more of a theoretical one. So let's suppose the internal energy is given by in a specific substance of a specific substance is given by this relation A plus B times PV. So the internal energy of a particular substance is given by this relation U equals A plus B times PV, where A and B are some constants. Determine the value of gamma for the above gas in terms of A and B. So basically, if this particular system or this particular gas is going a reversible adiabatic process, so which means you have PV to the power gamma equal to constant, and your internal energy is given by A plus B times PV. So I need to determine the value of this gamma as a function of A comma B. So how do I start with this kind of problems? So for this, I need to relate now whenever you ask questions like this, all you need to do is understand where this connection comes from. So how is internal energy? So PV to the power gamma equal to constant is a process. U is a path function. So this is not going to depend on the process. So now we have to relate that with this. So how do we relate that? So we have Q, we use the first law again, delta U plus work done. It is in a reversible in adiabatic process. So Q is going to be 0. So delta U is related to the work. So delta U is given by final minus initial states. That will be A plus B times final P2 V2 minus your initial state, that is A plus B times P1 V1, and this will be equal to the work done. Again, as we have derived before, I am just using the relation directly from there. Work done will be P2 V2 minus P1 V1 by 1 minus gamma. Like I'm just using the relation for the polytropic process, where in this particular case n equal to gamma for a reversible adiabatic process. So now if you solve this, so you have P2 V2 minus P1 V1 by 1 minus gamma is given by A gets cancelled. So it's a very straightforward problem. So this doesn't need much of a discussion, I guess. So we'll move on to the next problem. So this is more of a discussion one. You might have come across this scenario most of the cases. So imagine you are on a warm summer day and then you want to, in order to cool your room, let's say you do not have an air conditioner, and then you open your refrigerator. You open the door of your refrigerator. Initially, you will feel cool because of the air coming from the refrigerator. Now, can I use this strategy to cool the entire room? So instead of buying an air conditioner, I think I'll use my refrigerator itself. I'll use my refrigerator to cool my room. Can we go ahead with that particular strategy? Can we approach this problem using first law? So imagine this is your room. This is your refrigerator. So what is happening is if you're supplying power to the refrigerator, there is a work done on the system. So let's say your room is completely insulated or well insulated from the surroundings. In the event that it is well insulated from the surroundings, let's say your doors, windows, everything is completely closed, and all your walls are highly insulating so that you do not have any heat transfer from the internal to the external environment. So in that scenario, your Q will be 0. Now, if you apply first law, it tells you that delta U plus W should be 0 since Q is 0 and delta U is minus W. And in this particular case, we are actually connecting the refrigerator to an electrical supply from which your work is being done on the system. So this work is being done on the system. My system is this entire room, this entire thing. So which means W will be negative. So minus of a negative sign will be positive. So delta U is going to be positive. So if delta U is positive, which means your temperature will increase. Temperature of the system will increase. So why do you think this is not happening with your air conditioner? So even if you consider this is with a refrigerator, let's say you have an air conditioner, can you not approach the same process? So you have again the same room, you have an AC here, somewhere on the top, and again let's say your room is completely insulated. Again you are doing some work here, so AC is, if you recollect, if you connect AC to some power supply, so doesn't that mean you are spending some work here? Your AC is connected to a power supply, so which means you're again doing some work on this. But then you know that when you turn on your AC, you are, so since it is insulated, I'm saying Q equal to 0. So here again, if you follow the same logic as in the case of a refrigerator, so what would happen? So why is an AC cooling with a refrigerator the same? So is my approach wrong or something wrong here? There are two things to note here. Number one is it is not completely, in case of an AC, you have a port which actually takes air outside. And two, most of the split units that we have now is composed of two different units. You have an indoor and outdoor unit. The outdoor unit has the compressor, not the indoor one. And basically the work is being done outside. So this is having another outdoor unit. And this is where you're doing work and this is where you're rejecting heat to the external environment. So essentially your work done internally will be 0 and your delta U will be 0, which means your entire room temperature is being held constant. That is when you have your steady state. Once your steady state has reached, your entire room temperature will remain constant and delta U is going to be 0. But obviously, if some person is sitting inside the room and then he'll actually generate the heat and that will actually be sent out through your exhaust, and this will actually contribute to your heat loss. So your Q, instead of being 0, it will be some finite negative value. So that will be compensated by your work done, and then eventually you will attain your state where your delta is 0 and you will experience the cooling. In case of refrigerator, what is happening is we have this compressor and everything inside the building. So inside your room, you have a compressor here at the back of your refrigerator. In one of the old refrigerators, you can see a motor here, or basically a compressor here sitting here, and the sides of the refrigerator getting heated up. So the refrigerator cools the inside components and then rejects heat to the room. And this heat will actually increase the temperature of the room. So if you keep the door of the refrigerator open, then what is happening is it is trying to cool this entire room, but then it is rejecting heat again to the same room, which will actually not increase the temperature of the whole room. If for some reason, if you can reject this heat externally, so when this compressor is running and the heat that is being generated from the refrigerator, if you can somehow exhaust it outside the room by connecting it some to duct or something and then remove it from the room, in that scenario, then you can use this particular combination to cool your room. But as long as this heat is rejected into the same room as it is trying to cool it, then it is not going to give you a refrigerant effect on a longer term basis. I hope this is clear. Are there any questions? Okay. There are no questions. We'll move on to the last problem. So here you have ethane, which assume it to be a perfect gas. It's compressed from initial 1.1 parts per 27 Celsius. According to a polytropic process, the relation given by PV to the power 1.3 equal to constant until the final pressure is 1.6 bar. Calculate the heat flow to or from the cylinder walls. Molecular weight is specified and Cp is specified. So this is again a straightforward problem, just as we have done before. So I will be using the relations that we have derived previously. So we have PV to the power n, PV to the power n equal to constant. So from this you can relate PV power 1 minus n, T to the power n equal to constant, from which we can write P1 to the power minus 0.3, T1 power 1.3, P to the power minus 0.3, to the power 1.3, from which I can write T2 is T1 times P1 by P2 for minus 0.3 by 1.3, where P1 is the initial pressure, P2 is the final pressure, T1 is the initial temperature 27 Celsius converted into Kelvin, T2 we get from here. So you know the initial and final temperatures. So you can calculate the final volume as well. Like we know the initial and final pressure, so we can calculate the final volume also. The problem here is to calculate the heat flow. So if you recollect, we have derived an equation for heat flow as well previously. You can refer to the previous lecture, or we can have a couple of minutes, so we can derive that as well. So in case of polytropic process, work done is given by P2V2 minus P1V1 by 1 minus n. I can write this as MR, since it is a system approach, T2 minus T1. Use ideal gas law. Since it is a perfect gas, I can use that relation. I can write this as MRT2 minus T1 by 1 minus n. And your change in internal energy. Okay. Now we have the value of mass as 1 kilogram. And how do I calculate the value of R? So how do I calculate the value of R? There is 814. The molecular weight is given as 30. This is the value of R times T2 minus T1. So just dividing it with 1000 so that you will get in kilojoule. This is just for unit conversion. This is the work done. Again, the change in internal energy is again given by mCv delta T. So how do I calculate Cv? We know the value of R, 8.314 by 30 kilojoule per kg Kelvin. And we know Cp minus Cv is R. So Cv is given by Cp minus R. Cp is 1.75. This gives me 1.473 kilojoule per kg Kelvin. So I can directly use that here. So mass is specified as 1 kilogram, Cv is there, and initial and final temperatures are also specified. So we have we have delta U and W. So from this we can directly use the first law and get the value of Q, delta U plus W. Okay, are there any questions? Or if you want to use the same, if you want to directly remember some formula, you can directly calculate this from the original equation also for Q, where I can give you, so if you want to derive it, so how do you go about it? So W is given by mR T2 minus T1, or I'll write delta T by 1 minus n, and delta U is given by mCv delta T. So your Q will be given by delta U plus W, which will be m delta T R by 1 minus n plus Cv, you can write it as R by gamma minus 1. So how did I get this Cp? So because you can use the relation Cp minus Cv equal to R and Cp by Cv equal to gamma. From both of these, using both these relations, you can calculate Cv to be R by gamma minus 1. If you do that, so this gives us Q equals to mR delta T into gamma minus n by gamma. You can directly use this relation, or you follow the one that we have followed here. You calculate W using the polytropic process, and then you know initial final temperature. You can directly calculate delta U, use first law to get the value of Q. So whichever way you feel convenient. If you are good at remembering formulas, you can go with this, or you can stick to the notation of the way that we have followed. Are there any questions? Yeah, we have completed around 10 problems, so I think I have that's for the today. So we'll wait for a couple of minutes. So if you have any problems or any questions or anything that you want to discuss, we can discuss. Otherwise, we can conclude the session for today. Yeah, I guess there are no further questions. Thank you for joining. We'll meet again next week. We'll end the session for today.